Okay, good morning. This is the sixth lecture of the course Compressible Flow and Gas Dynamics. So, what we have done actually in the previous lecture, we have derived the integral form of governing equations. And when we derived the integral form, specifically we have considered the situation of inviscid flows. Okay. Now, we will try to see the applications of integral form of governing equations. Okay. So, and this application we will try to see an important application over here, which is known as jet propulsion. Okay. So, we will try to see jet propulsion application over here. So, do you know the basics of jet propulsion? The idea of jet propulsion is to generate the force for propelling an lift, and other term is thrust. Thrust is required to propel any aerodynamic object. Okay. So basically, if you see for the jet propulsion, we use different type of engines. For example, we name some as turbofan, turbojet, ramjet. So these are nothing but the different engines which are used for the jet propulsion. Then we may have some rocket engines for the rocket propulsion. Okay. So if you typically see a jet engine, can you tell me what is the ideal cycle on which these jet engines are based on from your basic thermodynamics course? What are different components of a jet engine? Tell me. Do you have any idea about jet engines? In aeroplane, what type of engines are used? Do we use reciprocating engines in aeroplanes? Then what type of engines? Have you heard of the term gas turbine? What is gas turbine? What is a gas turbine? Please tell me. Have you heard of Brayton cycle? Okay, so what Brayton cycle constitutes of? One, isentropic compression, then constant pressure heat addition, which is nothing but replica of a combustion process, and then we have isentropic expansion, and after that, in actual cycle, exhaust gases are just sent to atmosphere, whereas in case of an thermodynamic closed cycle, these are nothing but brought to the initial state by extracting heat from them at constant pressure conditions. So this is nothing but an ideal Brayton cycle. So ideal Brayton cycle is used in gas turbine engines. Okay, gas turbine engines can be used for two purposes. One is for power production and second for jet propulsion. Okay, when these are used for power propulsion, then entire all the gases are expanded till the lowest pressure in the turbine itself. Okay, and when these are used for jet propulsion, then part expansion of the gases is done in the turbine and part expansion in nozzle to create the necessary thrust. Okay, so this is very fundamental thing you should know, and whenever we use a gas turbine for propulsion, then the cycle is known as ideal jet propulsion cycle. Okay, so these are the basics of thermodynamics. So what I am doing over here, this is typically, if you see, I am trying to draw a gas turbine over here, or which is also known as a jet engine. Okay, now depending upon the different advancements in the jet engines, their names are turbofan, turbojet, ramjet. So these are depending upon the different advancements in the technologies. Okay, but basic idea is a gas turbine which is based on an ideal Brayton cycle. If it is used for power production, then all the gases are expended till the completely in the turbine. If it is used for jet propulsion, then part expansion is done in turbine and part in nozzle, so that it can create the necessary thrust force to propel the object. Okay, so if you see typically a gas turbine engine, I am trying to draw over here, so you will be finding some structure like this. Okay, this is a shaft, and on this shaft you are having some blades like this. What does these blades represent? What are these? Impeller. Is it a turbine or a compressor? So have you people studied basic thermodynamics? Then after this, what we will be having? What I have drawn over here, tell me. So this is the, if I tell you, this is the compressor section of a gas turbine. Okay, then this is the combustion section, and up to this point we have a turbine, and after this point we have nozzle. Okay, so in combined turbine and nozzle section we are having nothing but the expansion. Is this point clear? So this is inlet and this one is outlet. So what typically happens, gases will be coming. Okay, so atmospheric air will be taken at the inlet, and this atmospheric air is then compressed in this compressor. After it is compressed, its pressure and temperature will increase. Then it is passed through a combustion chamber. Okay, so inside this combustion chamber we will be injecting the fuel. What that fuel will be doing, that will be participating in an oxidation reaction with the air, and it will release its chemical energy. So upon the release of the chemical energy, after the combustion reaction has taken place, we will be having nothing but high pressure and high temperature gas. Then that high pressure and high temperature gas is partly expended over the turbine and partly expended over the nozzle, because our idea is to have jet propulsion. So why we are using turbine? Because whenever this compressor will compress the gases, so it will require work input. So we will consider the expansion in the turbine so that it is sufficient enough to provide the compressor work. At the same point of time, in any aircraft you will be having some other auxiliary inputs. For example, your control system, air conditioning system, lights, etc. So for that also you require energy. Okay, so we do expansion in the turbine which is sufficient enough to meet the compressor work as well as the compressor work and the power required for operating the auxiliary equipment. Okay, whereas the remaining amount of gases are expended over the nozzle, and the idea is to create more change in momentum so that more amount of force is actually generated in this particular direction so that it can propel in the forward direction. Okay, is this point clear? So typically in a jet propulsion system, gas turbine system is basically used. Okay, so if you have to determine how much is the thrust force that is created by this, okay, so what we will be happening when fluid is coming, some portion of the fluid is entering inside, okay, and some part of the fluid will also flow over the outer body of this engine. Is this point clear? What I am saying? So whenever aircraft will propel, part of the fluid will be going inside, which will participate in the actual process as a working fluid for operating this gas turbine engine, and remaining portion of the fluid which is coming from the free stream, that will pass over the body. Okay, so if you see, this particular body will be subjected to fluid forces from two sides. How? One is because of fluid pressure is acting on the external side, so there will be pressure as well as the shear. However, we have to remember one thing, for for compressible flow applications, we are considering or taking the assumption of inviscid flows. Okay, so considering the inviscid flow situation, we will be only considering that from outside we will be having what? Pressure that is acting from the outside, and particularly this is nothing but pressure of air, because outside we are having air only, whereas inside initially it is air, then it is becoming a high pressure air because of the compression process, and this high compression air, whenever it is participating in combustion, then it is becoming products of combustion. Okay, and then it is passing over turbine and propeller. So obviously whatever this inside fluid is there, that will also apply certain pressure on this. Is this point clear? And it means this pressure of the fluid is actually applying forces on the body of the aeroplane. Now obviously this will be giving us the resultant force, and that resultant force will also contribute into nothing but the thrust to propel the aircraft. Is this point clear? So it means if we have one gas turbine engine, or if we have an aircraft engine, so propulsion is created because of the surface forces acting on the body of the engine. Is this point clear? Is this point clear? So whatever the surface forces which are acting on the body of the engine, these will be actually creating the resultant force which is acting on the object. Okay, now when we will be talking about this resultant force, so obviously force can be because of pressure plus shear. So these are the two components of the surface forces which can act. Okay, whenever we will be talking about the thrust force, particularly the force which is generated in forward direction. Okay, so in order to propel the aircraft, so particularly if we talk about the thrust force, majority of the thrust force will be mainly due to pressure forces. Okay, mainly due to pressure forces, and contribution of actually shear forces is very less over here. Is this point clear? So in the thrust creation, contribution of shear forces is not much over there, so majority of the amount of thrust is mainly because of the pressure force. So that's why assumption of inviscid flow does not make much issues over here. Okay, so now if you see, if we have to calculate the pressure force, we can write F will be equal to minus surface integral of P into ds vector. Okay. So the point is, if you see now, this is the outer surface. This whole outer surface is exposed to this outside air pressure. So we should know the pressure distribution over this outside surface. At the same point of time, from inside also some pressure is acting on the wall. At the same point of time, some pressure will act on these other objects also. For example, this is a combustion chamber. So in combustion chamber, we will be having complicated geometry. So on the surface of the combustion chamber also, because of the hot gases, some pressure will act. Okay. Then in nozzle surface also some pressure will act. So ultimately, if we see, uh, one can think of that if we have to calculate the force on this body of the engine, one has to determine the pressure distribution at each and every component of this engine. Okay. However, the within the combustion chamber there can be very intricate geometries, as well as the shape of the propellers of compressor and turbines will be so intricate that exactly determining the pressure distribution, surface pressure distribution, is an complex and complicated problem. Okay. So what we do over here, if we just take the integral form of governing equation, that integral form of governing equation can provide us very simple and straightforward expression for the thrust uh, acting on an aircraft engine. Okay. So let's try to see how the application of the integral equation results in actually simplified formulations, and we need not to deal with each and every surface pressure distribution of the intricate components. Okay. So for that sake, what I will do, I will just replace this internal structure of the object, and in place of this internal structure of the object, we will only deal with the pressure which is supplied by gas on the outer body of the aircraft. Okay. So what I am saying is, I have considered, say, this is my one branch and this is the lower portion. Okay. Now what I will do, I will say that in this portion what will happen, here I will be having compression, here I will be having combustion, and then I will be having expansion. By knowing these three major phenomenon, what I can do, I can actually draw the pressure distribution on this body. Okay. So let me try to draw the pressure distribution now. So what I can do, I can consider that so this is my object. Okay. So at the moment I am considering that outside atmospheric air is applying a pressure of P infinity on the body of this aeroplane. Okay. So will this statement be true always? If you see, your aircraft is under motion. Okay. Then outside pressure distribution because of the fluid will not be exactly equal to P infinity. Okay. Why? Because there will be somewhere acceleration, deceleration of the fluid, and pressure distribution will be different than the free stream pressure. Okay. But if we consider that our engine is not yet installed, okay, it is just lying in atmospheric condition, in a stationary condition, then obviously the air outside it will be in stationary condition, and this will apply a uniform pressure. Okay. So consider that if I have drawn anywhere wrongly, consider that size of these arrows should be same, because we have uniform pressure which is acting. Okay. So when I am considering the uniform pressure, I am considering that air is not in motion. If air is not in motion, it means we are calculating the thrust for an engine which is not yet in operation and which is not yet installed. Because when you will be installing the engine in the body of an aeroplane, so you will be finding that some portion of the surface is actually connected to the housing of the body also. Okay, so it means whole surface is not exposed to the pressure P infinity. So that is the reason initially what we are considering, that say we have symmetry everywhere in the engine body and air outside it is stationary. So it means this is situation of nothing but an uninstalled engine. Okay. That is why whatever the thrust we will be obtaining over here, we will be calling that thrust as uninstalled engine thrust. Is this one clear? Whatever I mentioned, is it clear? So we will be calling this thrust force as nothing but the uninstalled engine thrust. The reason is because we are considering everywhere the uniform pressure distribution. Okay. Now I can consider that this is my body. So this is the say outer control volume of the fluid which is applying pressure P infinity over here. Now I can have inside also some pressure will be acting because of the inside gas. So initially gas will have pressure close to free stream. Then because of the compression process, this pressure will keep on increasing. So you see, I am actually increasing the size of the arrow over here. Okay, so this pressure is increasing. After that, for some moments, it will remain constant. Why? Because of constant pressure combustion process. Okay, and after that what I will be having? I will be having expansion. Then with expansion actually it will keep on decreasing. Okay, so your pressure distribution, if you see, it is something like this. Okay, so this is the internal pressure distribution, say Pi. At the inlet, say I have I condition, at the exit I have say E condition. Okay, so at the exit I have pressure as P exit and velocity as V exit. And at inlet, let's consider that our fluid is entering almost at the free stream pressure. So at the inlet I have pressure as means Pi equal to, sorry, I should not use Pi because Pi I have used for the internal pressure. So at the inlet I will simply say I have pressure P infinity at entry point and velocity as say V infinity. Up to this point, is it clear? Now if I have to calculate the force which is acting on this engine, that will be equal to minus integral of P into ds vector. Okay, and if you see, we have two kinds of pressure over here. One pressure is acting from the outside which is having constant magnitude. So I can write minus double integral of P infinity into ds vector, and I have some internal pressure which is acting on this inside surface. So I can write minus double integral of Pi and ds vector. Okay. Now this F resultant force which is acting on the engine, this can act in this resultant force can be at any angle. Okay. What I will do over here, I will specifically try to derive the expression for the thrust force. Okay, so thrust force will be particularly applicable to propel the engine in the forward direction. So this is my forward direction over here. Okay, let's consider this is the positive x direction. Is this point clear? So positive x I am just considering by considering the fact that it has to propel in the leftward direction because of the fluid pressure. Okay, so this is my positive x direction I have considered. Now as I told you that I am only interested in finding out the thrust force. So I will calculate the only x component of this force. So thrust will be nothing but the x component of this particular force. So when I am referring to that particular component, I can simply say that minus P infinity into this ds vector I am having, I will only consider the x component of this ds vector. Okay, and similarly here also I will consider the x component of this dx vector. Up to this point, is it clear? Now this integration is challenging. Why it is challenging? Because this portion pi, this pressure pi is actually variable over here, and we don't know the exact surface pressure distribution for pi. So that's why for the time being, let us hold this integration, and specifically let's try to integrate the first term. Okay, so if I integrate the first term, that will become, let me number this equation as 1. Now what I have done, I have considered the first term of equation 1. So if I consider first term of equation 1, that becomes P infinity, and then I have ds x. Okay, double integration, and over here what I can do, P infinity I can take outside because P infinity is constant throughout the body, and simply I can say double integral of ds x over here. Okay, now as I told you that this dsx, when I am considering, I have to consider the x component of the area. Okay, so over here if you see on this external surface, because I am now talking about P infinity, so when I am talking about P infinity, I am talking about this external surface. So you can see that pressure is in this direction and surface area vector will be in this direction. Okay, so both are opposite to each other. So if both pressure and surface area vector are opposite to each other, so that is one point. That is why we have already negative sign outside. Another interesting point, you will come to know that this portion, actually I might have drawn this profile with not very accuracy, but if you see, the exact profile is something like this. So this is the portion of area which is giving normal in this direction, and then remaining portion of area is always giving the normal in right direction. So if you see, the major fraction of the area is giving normal in this particular direction. Okay, so that's why whenever you will be calculating the total surface area vector, its direction will be dominant in this side. Okay, is this point clear? So total surface area vector will be dominant in this direction. If you consider that total surface area vector is dominant in this direction, its x component will be where? Towards the right side. Okay, its x component is towards the right side, whereas positive x coordinate we have considered towards the left side. So I have to write this dsx component with negative sign. Is this point clear? Profile of this airplane engine is such a way that this projected area is very less and this projected area is more, so net vector will be in the this direction. That's why this x component will be towards the right direction. Okay, and can you tell me now what will be the net projected area in x direction? If you take projection of this, if you take projection of this, what you will be getting? You will be getting a circle over here, and this circle will be of area AI. You will get one small circle over here, and this small circle will be of area A E. I is inlet, So cross sectional area of this circle will be say AI, and cross sectional area of this end circle is AE, and this area enclosed will be the net area vector in this net component of area in x direction. Is this one clear? Am I clear with this? So what you have to do, you have to take the projection. If you take projection of this, you can see some area of this solid object is there in the above portion, but in this area this net projection from this side and this side are actually cancelling out. Okay, so net area which is remaining, that is this particular portion over here. Okay, and that portion is nothing but AI, projection of that in x direction is AI minus A. Is this one clear? So I can say that my dsx integral in x direction is nothing but equal to minus of, minus because it is acting in the rightward side, minus of AI minus AE. Is this one clear? So what I can do, I can write this P infinity into ds integration as P infinity times minus of P infinity times minus of AI minus A, which I can simply write as P infinity times AE minus AI. Okay. So say this is my equation number 2. So later on I have to substitute this equation in equation number 1 only. Up to this point, is it clear? Okay. Now this is the second term, and for estimating the second term I should know the internal surface pressure distribution. Okay, whereas this internal surface pressure distribution at the moment is not known to me. Okay, so if it is not known to me, then how I can further proceed? So what I will do now, I will try to consider one interesting situation. Okay, so this is my body, this is the solid body on which gas is applying pressure from inside, and that pressure is Pi. Similarly, if I consider a fluid control volume over here, okay, inside fluid control volume, what I am doing? I am just considering the inside fluid control volume. Okay, so for inside fluid control volume, that control volume will look something like this. This will be my fluid portion. So if this inside this Pi was the pressure which was acting on the body, then this body will also put equivalent amount of pressure on this control volume. Is this one clear? But in opposite direction. So I can say that I have some pressure over here which is acting on this control volume. So this will be the distribution of pressure, something like this. This is just replica of Pi. Okay, and here I have already considered our pressure is P infinity, velocity is V infinity. Here pressure is PE, velocity is VE. Like this, there will be pressure from bottom side also, that I am not drawing over here. So say this is my control volume A, B, C and D. Okay, now this is a completely a fluid control volume. So let's now apply the momentum equation for this fluid control volume. If I write momentum equation for this, first thing is this is a steady state situation. Okay, flow is not changing with time. So my temporal term of the momentum equation will vanish. So I will be having rho v vector dot ds vector multiplied by v vector. On the right hand side I will be having the pressure force. So minus surface integral of p into ds vector. Then I have envisaged situation, and at the same point of time, because we are referring over here to the situation of thrust force will be mainly because of the pressure distribution. That's why we will not consider over here the body force also. Is this point clear? So body force also I will not consider over here. Is this point clear? Now if I extend this equation for x direction, because we are trying to find out the force only in the x direction. So if I extend this equation for x direction, I can say that rho v vector dot ds vector multiplied with x component of velocity, its surface integral, that will be equal to minus surface integral. In place of p I can write pi over here because my pressure distribution is pi, and in place of area I can write only the x component of surface area dsx. Up to this point is it clear? Now let's try to find out this particular equation. Okay, so if you see this closed surface integral, this control volume is having how many surfaces? One is A to B, then B to C, C to D, and A to D. So this control volume is having 4 surfaces. So I can divide this surface integral, cyclic surface integral, as nothing but the surface integral for AB plus surface integral for BC plus surface integral for CD plus surface integral for AD. Okay, like this I can divide this closed integral. So now if you see I have this first term. Let's first take the first term of this equation number 3. Okay, this is equation number 3. Remember these equation numbers also we will be using later. So first term of equation 3 says double integral of rho v vector dot ds vector times vx. Okay, now this will be equal to integral for AB, A to B. Can you tell me what will be integral for A to B? Integral for A to B, rho v bar v vector dot ds into vx. Is there any mass which can pass through this A to B boundary? Because A to B boundary is nothing but adjacent to a solid wall, and through solid wall, if we are considering an impermeable solid wall, then there is no mass transfer. If there is no mass transfer, then momentum transfer also across this A to B boundary will be 0. Okay, so I don't have any momentum transfer across A to B boundary. Similarly for C to D boundary also I will not be having any momentum transfer. Okay, so what I am saying over here, that integral rho v vector dot ds vector times vx, this will be 0, and this will be and plus one more integral term which is from C to D, rho v vector dot ds vector into vx, this will also be 0. Okay, so these two quantities will be 0. Then I will be having now the rho v vector dot ds vector for the left face AB 8D. So if you see, this is your inlet face A to D. Here velocity vector is something like this. This is the V infinity, and area vector AI is like this, because area is always in the outward normal direction. Okay, so if you take the dot product of V and ds, both of these are in which direction? Opposite direction. So I will get, and density over here is say rho infinity. Okay, so I will write rho infinity times, and V dot ds dot product will be nothing but minus AI into V infinity. Is this one clear? Because area vector is in outward normal direction and velocity vector is in inward direction. So two vectors are having 180 degrees angle. Okay, so when I will be taking the dot product, cos of 180 will become negative, minus 1. Okay, so I am having minus of AI in V infinity over here. Okay, after this, what I will be having? I am having x component of the velocity. Now positive x direction I have taken in this side, and my velocity vector, x component of velocity vector is in the right side. So here also I have to put minus sign. Okay, remember this point very clearly. We are dealing with the vector notations, so sign is having huge importance over here. Whenever you are dealing with the vector notation, then sign is having huge control on the overall physics. Okay, so please don't use the wrong sign notation. Okay, then plus we have to now consider the outlet surface. So outlet surface is my B2C. For B2C surface, if you see, this is the area vector AE and this is velocity vector VE. Both are in same direction. So I can simply write, if rho E is density of gas at the exit boundary, then rho E times, both are in parallel direction, so dot product will be positive, AE into VE times, we have to now multiply the x component of the velocity, and that is in rightward direction, which is opposite to the positive considered direction. So that will be nothing but minus of V. And ultimately I will get from here rho infinity AI V infinity minus of rho E AE VE times V. Okay. Now if you see, what is this? Mass flow rate. So simply I can write m dot I into V infinity minus m dot E into V. Okay, so this is the expression for first portion of equation 3. So let me write this as nothing but equation 4. Is this one clear? Now if I substitute this in equation 3, what I will get? Okay, before that let's try to first see the another portion. I have to also calculate the right hand side, which is pi into ds x. Okay, then I have closed integral of pi into ds x. This also I have to split into 4 components. Okay, because I have 4 components over here. So this will be, say, integral for a to b pi ds x plus integral from b to c plus integral from c to d plus integral from a to d pi dsx. Okay, so now if you see a to b, This is my A to B. Pressure at A to B is P infinity. Oh, sorry, A to B is this one. Yeah. So this is my A to B. So at A to B, I have some pressure variation, and at the moment I don't know this pressure variation. So what I will do, A to B, I will consider at the moment like this only. Likewise, C to D also at the moment I will keep as it is. Okay. But this A to D and B to C are something which I can actually calculate. Okay. Why? Because if you see the surface A to D, at surface A to D, I know the value of pressure. So value of pressure is P infinity, which is acting like this, and my area vector is A. What is the area of this A to D face? AI, and that is acting in, okay, backward direction. I can say positive x direction. So first let me write these two terms first, which are remaining as it is. So as it is, term is A to B PIDS plus C to D PIDS x. These I cannot change. Then I have B to C term. So if you see B to C face, here pressure is acting like this. This is the PE pressure, and outward normal vector will be like this, AE. And AE is moving in nothing but negative x direction. So that's why I can write this as, and pressure throughout is constant. So pressure I can take outside the integration, which is becoming PE, and integral of ds x for B to C will become minus AE. Is this one clear? Is it clear or not? Please tell me if is it clear or not. So AE is the area of that outlet, and it is in rightward direction, which is opposite to the positive x direction. Okay. Then I will be having PI from A to D dsx. So if you see in face A to D, I have pressure nothing but P infinity, and area vector is in which direction? Positive x direction, and its magnitude is AI. So I can write this as P infinity as the constant pressure at the outside, and area vector I can simply write as AI. Okay. So this is my equation number 5. Now let's substitute equation number 4 and 5 in equation number 3. If I do so, what I will get? If I substitute 4 and 5 in 3, what I will get? I will get equation number 3 as, please tell me fast. This is 3. So first I have to substitute over here equation number 4. So equation number 4 is m dot I V infinity minus m dot E VE. This will be equal to how much? Minus of Pi into dsx. Okay, minus of Pi into dsx, and that I have just now calculated. So Pi into dsx I have calculated. So minus of this will be with negative sign. So that will become, what I can write this? This will become positive. So PE into AE minus P infinity into AI plus double integral, plus or minus? Okay, it will come minus now. Yes, minus sign is there. Yeah. So it will come minus of double integral A to B Pi dsx minus of double integral, sorry, C to D This pen is not working today properly. Pi dsx. Okay. So this is equation number 3. And one more equation I was having at the back. That was equation number 1. And equation number 1 will become, if I substitute this 2 into this, so equation number 1 will become t equal to, in place of this integral p infinity ds, I have to write p infinity into ae minus ai. So with this minus sign, that will become ai minus ae, and then I have this integral also over here. Okay, so if I write equation number 1, please tell me what I will get. T equal to p infinity times, have you not remembered, ai minus of integral pi into dsx. Okay, now remember one thing. What was this term? This term was force on solid, means engine body, due to gas pressure. Okay, so this was nothing but the force on the solid due to gas pressure, and this was acting through faces A to B and C to D, and this term over here is nothing but force on gas due to solid body. Is this one clear? What is this? This is force on the gas due to the solid body. So both the forces will be same, but they will be having the opposite direction. So what I can do, this entire term, which is force on the gas due to the solid body, I can tell that, so say, let me write it, minus A to B integral of pi ds x minus integral of pi dsx from C to D. This is the force on the gas due to the solid body. This must be equal to minus double integral pi dsx, which is force on solid due to gas. Is this one clear? And over here, this is nothing but force on gas due to. Is this one clear? So it means this last term of, say, this is my equation number A, and say this is my equation number B. So last term of equation A is nothing but minus of last term of equation B, or I can say in other way that last term of equation B is nothing but minus of last term of equation A. So now what I will do, I will substitute minus of this term from the equation A into equation B. Is this one clear? So if I do so, then what I will get? T equal to P infinity into AI minus AE, and in place of this second term, what I will do, I will write minus of this term. Okay, so if I write minus of this term, that will become PE. Tell me what I will get. Plus PE AE minus P infinity and then this will become with negative sign. Okay, minus m dot I V infinity. Is this point clear? Plus m dot E into V. Are you understanding what I have done? Basically, what is this? This term is nothing but minus of this. So minus of this I have calculated and that I have substituted in B. Okay. So that, now tell me finally what I will get. T equal to m dot E into VE minus m dot I V infinity. Okay. And this P dot infinity AI will cancel. I will get AE is common. AE times PE minus this is the simple equation of a not thrust, uninstalled engine thrust. Okay, why uninstalled? Because outside we are considering nothing but the atmospheric pressure, uniform pressure distribution, whereas in actual running engine outside pressure distribution will not be P infinity. Okay, and you can see the beauty of this momentum equation over here. So what I have done, I was having simple force expression integral of PdS. In that expression of the force, what I have done, in that particular expression of the force, I have just substituted that with the momentum of the gas by employing nothing but the integral form of the momentum equation. Okay, so if you see the physical meaning of this particular thrust force equation, what is m dot E into VE? This is the outgoing momentum at the exit point. This is incoming momentum at the inlet. So net rate of change of momentum in x direction, okay, across the engine. So this is nothing but the net rate of change of momentum across x direction. So that will give some force plus what is the change in pressure, that is also contributing some force. Okay, is this point clear? So physically also you can relate it. The first term is net rate of change of momentum in x direction, that is acting that is giving one force, and another force is because of the changes in pressure within the engine. Okay, so this is how you can see how the integral form of the governing equation actually has helped us in finding the thrust force, uninstalled engine thrust force. Okay, so earlier if you have to if you don't use the momentum equation, then one has to first exactly find out the this pressure distribution, this particular pressure distribution over the surface. Okay, but by using the application of this momentum equation, this pressure force which is acting, that has become nothing but the rate of change of momentum, and ultimately it has helped us in giving the simplified thrust equation in the form of algebraic equation without even knowing the actual surface pressure distribution. Okay, so that is the beauty of the integral form of momentum equation over here, which we have actually just now seen. Okay.